Well, good evening, everyone, and welcome back to this, our final Our Universe Reveal before we take a pause from our talks for the summer. My name's Jonathan Crass, and I am the coordinator for this, the public lecture series from the Department of Physics at the University of Notre Dame. Thank you all for joining us this evening. We'll have our usual online format again tonight with a presentation followed by answering audience questions. You can submit questions at any time, either as we go along or at the end of the presentation. To do that, if you're on Zoom, you can submit those questions via the Q&A button at the bottom of your screen. Or if you're watching via YouTube, you can use the chat window on the right-hand side of your video. You can also, on either platform, use the link to the Google form, which I'll post into them shortly. Tonight, it's my absolute pleasure to welcome back one of our regular speakers to Our Universe Revealed. Dr. Keith Davis is an assistant professor of the practice in the physics department at Notre Dame and is the director of the university's Digital Visualization Theatre, or as we tend to call it, it's a little easier to say, the DVT. This facility, situated on the campus at Notre Dame, and which many of you have possibly been to previously for our regular attendees, immerses attendees in a high resolution and high fidelity images rendered in real time on a 50-foot diameter dome. It allows new perspectives for teaching topics in more depth ways. And for those of you who've been able to visit it previously, it really is a fantastic resource to have. Keith himself, before coming to Notre Dame, he received his PhD from Clemson University, studying the interaction between supernova explosions that we heard about in previous talks and molecular clouds using computer simulations. Today, as well as coordinating both the DVT and its activities, he creates educational content for teaching both within science subjects and more broadly. And tonight, he's going to talk about one of the most challenging measurements in astronomy, and that is figuring out just how far it is to the objects we're looking at. So Keith, thank you very much for offering to speak this evening, and let's see if we can get your screen share all working.
All right, happy to be here. Let's go ahead and share my screen, and I'm going to actually just share the desktop here because I'm going to be switching around doing some traditional PowerPoint, but also using a couple of tools. Everything working so far? You can hear me, Jonathan?
Yep, all looks great. Over to you.
Okay, great. So thanks for joining us tonight. If this is your first time watching me give a talk on Zoom, please keep in mind that because the DVT has a strong outreach mission as part of what we do, I have, over the course of our isolation in our homes, been doing some public talks on Thursdays. So it's been every Thursday at 1:30 and at 7 p.m. So 1:30 p.m. and 7 p.m. I may be changing that schedule soon. I know Jonathan is going to talk to you about possibly getting onto an email list that he runs. If that happens, we will also be creating a DVT email list, so we can get you on that as well if you would like, because we're probably going to be taking a break just like Jonathan's taking a break as well. We've all been giving a lot of talks lately as we've tried to make sure that everyone's education continues to move forward. And we really want to give you all a chance to learn in the time that some of us have a lot of extra time. So that's what I've been doing during the breakdown. But what I want to do today is start to tell you a little about how we measure how far away things are. And so I've titled this talk, Climbing the Distance Ladder. And I'm not really going to tell you what the distance ladder is today. Well, I'm going to tell you today. I'm not going to tell you at this moment. I will that will be revealed as we go on. So there would be a better time to explain why we call it the distance ladder. But as you look out at the sky, it turns out that it's really, really hard to measure how far away an object is. And that includes measuring the distance to an object even as relatively close as the sun. Now, you wouldn't think of the sun as being that close to the Earth, but compared to the other stars, it is. And even measuring that is really quite hard. So the reason that I thought this would be an interesting talk to give is there are two events in the last year that are related to astronomical distance measurement. And one of those was that there was a transit of Mercury on November 11th. 2019, so just last November. Unfortunately, although we had worked to plan a public event for that, it snowed like crazy that day. So we did not get to see the sky at all, much less this neat little astronomical event. And the thing about astronomical events is you can't pause them and you can't reschedule them. If you miss it, you just miss it. The other is that April 28th of this year was the 100-year anniversary of the Great Debate, which is also called the Shapley-Curtis debate. It was two very famous astronomers of the time were arguing, have a very public argument about the nature of what they called spiral nebulae. One side of the argument was that these were simply clusters of stars and gas within the Milky Way, and that the Milky Way was a large proportion of the universe, if not all of the universe. But the other side was that those little fuzzy, swirly spiral nebulae were so far away that even though they look small, they must be large enough to be of commensurate size to the Milky Way, and that the Milky Way was just one galaxy of many others. And that's what we were really seeing with these spiral nebulae. Now, you probably already know the answer, but remember, it was literally only 100 years ago that some of the best astronomers of their day that had access to the absolute latest data were still arguing, and reasonably so. In fact, I'm not going to go too much into the details of the debate, but researchers and historians that have looked at it have realized that both of them were a little bit right and a little bit wrong, which is not surprising. And it was really further measurement that allowed them to finally settle out. So I want us to start with a couple of tools that I'm going to use to illustrate some of the things. And I like these tools because I'm used to giving presentations in a planetarium, which means that I can show you anything I want at any date in the sky. I can take you all the way to the edge of the universe and back. I can't do that with the desktop, but I do have a couple of tools that can help me simulate the night sky. And the advantage of these tools is that you can download or work with these on your own. So the two that I'm going to use tonight are on the left, you see NASA's EYES. And there are several different versions. What I will be using is the one in the middle at the bottom you see there. I'll put my mouse over it to highlight it. Eye is the eyes on the solar system. So I'll use that to represent the positions of things in the three-dimensional space of the solar system. On the right, I'm going to use the web version of a product called Stellarium. And by the way, I have no affiliation with either of these. I just think they're useful. Stellarium is a downloadable project, and the downloadable project has a lot of extra options, but I like to use the web version when I'm presenting because I think controlling time in the web version is a lot simpler than the way that you control time in the downloadable version. There are some challenges with it, but I think it's a nice version. So if you're interested in being able to play with any of the things that I've used to teach you today, please take a look at Stellarium Web or eyes.nasa.gov, and you can download or use these products. So what I want to do now is just show you what a transit of Mercury is, talk about why it doesn't happen every time the Earth and Mercury line up, and then this is my reminder to go to timeanddate.com and show you how to calculate or find these sorts of interesting dates in astronomy. So let me switch over here. Jonathan, please break in if for some reason the sharing doesn't switch over to the new desktop. On the right, you should see Stellarium Web, and on the left, you should see that eyes on the solar system. So I'm going to start with this on the right, and it's set to pretty much now, and it being 7 o'clock. You can see that the sun is still up. If I zoom out, I can get a better view of the sky. I can move around to look at the ground, and it will allow me to see through the ground to see where the stars would be. I can drag things around to look at different places. You can see that I have highlighted the constellations. I'm going to go ahead and remove those real quick. I can zoom in. I can do all kinds of fun things. So this is intended to represent what you would see if you were to stand outside and look. So if we were to look west right now, we would see the sun. We would probably not actually see Venus here, but it has gone ahead and labeled it for us. If I drag time forward, you can see how the sun is setting pretty far to the north of west right now. If I keep going, eventually you can see Venus just on the horizon. And if you're lucky, or if this tree wasn't in the way, you might be able to see Mercury as well. I can even click on Mercury, and it should bring up an idea, a little information to tell me how far away it is. It's a little under 1 astronomical unit away, and about its magnitude is about -10. I'm not going to go into what the magnitude numbers mean right now. Okay, so if I click down here, though, well, that brings up location. That's not what I wanted to do. I want to click over here and bring up the date. And just to show you what the transit of Mercury would have looked like, so that everybody's on the same page with what I'm talking about here, I'm going to jump to November 11th. Actually, I'm going to go to the 10th because I think that's the way this works out. And then I want to center on Mercury. So to find it, I'm going to type in Mercury and then click it, and it should see, of course, it's below the horizon right now. If I drag time forward, it should rise. And if I zoom in, you can see there's Mercury right on top of the sun. Now, this is what's called a transit. And what that means is that from the perspective of those of us living on Earth, one object is transiting or crossing in front of another object. In this case, Mercury is transiting the sun. There are other very famous transits, if you've ever heard of an eclipse, and I'm sure that you have. When the moon moves in front of the sun, we could say that it transits the sun, but we usually just say that it's an eclipse or that it eclipses the sun because it blocks the sun, right? Mercury is not large enough to block completely the surface of the sun, so we will instead say that it transits the sun instead of eclipsing it, although it's kind of the same phenomenon. So now as we watch here, you can see how it moves in front of the sun. I'm going to zoom out just a little so you can see where that tiny little dot is on the face of the sun. Whoops. I moved things and it lost the focus on Mercury. But hopefully you can see how easy this system is to use. It zipped right back neatly. And now you can see, now the sun's going to seem to move a little oddly because I'm actually locked on Mercury. And then if it splits the day during the daytime because it's an astronomical product. So if I move over, then we can see that it moves past. All right. So why does that happen? Well, if you move to the left to NASA's eyes on the solar system, we can zoom in here. I've got it set to today, but again, just like the other system, I can type in 2019, November 11. And if we find the Earth here and kind of line up, you can see there. And I think I'll go ahead. Let's actually center ourselves on the Earth and zoom in on it. Zoom out just a touch and then line ourselves up so that we can see how, from the perspective of Earth, Mercury is about to cross in front of the sun. And it may not line up perfectly because we're not actually on Earth. And the dates are a little funny, but I think you can see there that it does seem like it crosses the face of the sun. Now, of course, that's because we zoom back out here. We see that the sun, Mercury, and the Earth are in a line, right? So that's where Mercury has to be. It must be in what we call conjunction with the sun. This would be the conjunction where there are two conjunctions. This is the one where it's on this side of the sun, obviously. It's on the other side, it would seem to go behind the sun and wouldn't block it. So that's a Mercury transit. So unfortunately, we didn't get the chance to see that in November because it was snowing here. But these are a little more common than some other transits, which I'll talk about in a moment. The next thing I want to do is if we center on the sun again to bring it to the center of our view, and NASA requires me to zoom in here, but if we back out, you should be able to see if I speed up time how Earth and Mercury are constantly moving around the sun. And if we check the date here, they will line up again in February. They did line up again in February of 2020. Now, we did not, however, have a Mercury transit in February of 2020. And I think if I line things up, you might be able to see why. Zoom in just a touch to get some of those out of the way. If I highlight Mercury's orbit, you can see that it seems to be kind of tilted. And it is tilted compared to the plane that the Earth and the Sun are on. So because it's tilted by a few degrees there, most of the time when we line up, Mercury seems to go either in below or above the Sun instead of across the Sun. And that's why it doesn't happen. Even though we line up with Mercury in between us and the Sun fairly often, we don't actually get everything to line up just right so that Mercury seems to go across the Sun. So what was that date? February 26th, somewhere around in there, actually. It's time to switch over to timeanddate.com. So if you want to find information about transits or other things, I think Time and Date, again, not affiliated with it, does a great job of building educational tools to kind of illustrate how this works. They also have a nice little list of the dates that would happen. So the next few transits for Mercury are labeled here. We see one in 2032, 2039, 2049, 2052, and 2062. So these are a little more common. You can see that, so there's one in 2019. It's going to be a little while before 2032, but then it's only 7 years to the next one. So transits of Mercury are actually somewhere between 7 or 8 to about 10 or 12 years, typically on average. And those happen pretty often. Okay, so that's an example of one kind of transit. So when Mercury passes in front of the Sun. Now, you may be wondering, what on earth does that have to do with figuring out how far away the size of this, how far away the Sun is, or how big the solar system is? So as we look at the Sun, we can see that it moves, and we can see that the other planets move. And for thousands of years, we've been trying to predict the motion of those planets. But it's really going to take a little bit for me to explain why that's important. So bear with me as a moment, though. I do want to make sure you get a sense of what it looks like to actually see Mercury cross the Sun. This is an image taken by John Schumack from galactikimages.com. I just thought this was a really pretty one. I think this one was hosted on Astronomy Picture of the Day. You got a tiny little dot of Venus moving in front of the Sun. I think this is a really well done image. We come down here. Here's a zoomed in image. This one is taken by Wise Imaging. You can see there's the Sun. I like this one because it's zoomed in enough that you can see some of the granulation on the surface of the Sun. That's convection cells as the Sun boils, which is pretty exciting. I'm going to move down here. Here's an animation of it. This one was put together by one of NASA's orbiting observatories that watches the Sun and measures things about it. This takes a few hours, by the way. Let's watch that one more time. So that's what it looks like when a planet like Mercury transits the face of the Sun. Okay, so now we're all on the same page about what a transit is. What on earth does a transit have to do with measuring the size of the solar system? All right, so here's a little bit of history. Now, this is not a historical talk. I am not a historian. What I have done is done a little bit of research and put together a little timeline that is related to our ideas about the size and scale of the solar system. This is just for reference. This is not the core of what I'm teaching. But I wanted to bring up the idea that 270 BCE is the first record we have of someone proposing that the Sun might actually be the center of the solar system. So I think that's interesting. That is mostly ignored. In 140 CE, Ptolemy put together a model that put the Earth at the center of the solar system, which was really the way that everybody thought it was. And this model used a complicated gear system to explain why the planets seemed to go backwards. But it was useful for predicting where the planets were going to be in the future. This is something I learned doing this research. I know very little about this, but there was an Indian mathematician in 499 that actually described and did calculations with gravitation 1,200 years before Newton worked out the formal mathematics of gravitation. So there was a lot of really interesting work going on there that Europeans weren't aware of, which is why we put our dates a little later for that. But I thought that was really interesting, so I wanted to include it. Now, in 1543, Copernicus published his heliocentric model. But I think what's important to understand about that model is that it still kept the planets on circles. It put the sun at the center, and it explained some aspects of the motion of the planets in a simpler way. But what it did not do is do a very good job of accurately predicting their position, which is one of the reasons that it was challenging to accept it. So after that, though, Kepler managed to use data by Tycho Brahe to publish his 3 laws of planetary motion, which I'm not going to go into the details on. But one of the primary things he realized is that the planets were not on circular orbits, they were on ellipses. And that allowed him to make predictions that were better than anyone had ever been able to make before. And that's why his model was eventually accepted, was because it predicted where things would be. And that model gave them the accuracy necessary to predict that Venus would pass in front of the sun in 1631. So he made that prediction in 1629. What he didn't realize, though, is that there would be, Venus transiting the sun would actually happen in pairs that are about 8 years apart. And then it's somewhere around about 100 years for the next pair. Okay, Jeremiah Horrocks observed the transit of Venus in 1639. He improved upon Kepler's model and then also recognized that they occur in pairs. 1687, Newton manages to work out gravity and build a formalism that connected the motion of falling bodies on Earth to the motion of the planets in the sky. But here's a key part of this. That model gave an order for the planets, and it gave their positions, and Kepler's model allowed you to calculate where things would be in the future. But it was all done in terms of ratios, not in terms of absolute distances, because they did not know how far away the sun was or how far apart the planets were. This is a plot of the numbers that Kepler used in 1618 when he was building his model. That's really mean distance from the planet to the sun, you can see up here. But note that the Earth is defined as 1. It is simply 1 away from the sun. And that's our familiar unit that we use in the solar system called the astronomical unit. And now we have a number for that. We can attach a measurement on Earth that we might make in miles and tell ourselves how many miles it is to the sun. But Kepler's model could not do that. It allowed for calculating the ratios. And in fact, I don't want you to pay attention to all this period information. What I really want you to realize is what this model could say is that if the Earth was 1 unit away from the sun, then Venus was 72% that distance. Mercury was about 39% that distance. Mars was about 1.5 times that distance. And Jupiter was 5 times that distance. And Saturn was about 9.5 times the Earth's distance from the sun. So the geometry was available to figure out these ratios. But you had to measure one of these in order to figure out what the others were. But you had no way to do that, because how do we usually measure things on Earth? Well, what we do is we take something we already know the distance of and lay it down next to something, right? And that's primarily a lot of what we do to measure the distances on Earth. Unfortunately, we don't have any rulers as big as the solar system that we can move around. So what they needed to do was come up with a geometric measure that would allow them to measure the distance to the sun. This is a book that I read to help me understand how this works, called Chasing Venus, The Race to Measure the Heavens, written by Andrea Wolf. And I would actually like to read her introduction to the book for you. It's just a little paragraph here. In 1716, British astronomer Edmund Halley published a 10-page essay which called upon scientists to unite in a project spanning the entire globe, one that would change the world of science forever. On 6th of June, 1761, Halley predicted Venus would traverse the face of the sun. For a few hours, the bright star would appear as a perfectly black circle. He believed that measuring the exact time and duration of this rare celestial encounter would provide the data that astronomers needed in order to calculate the distance between the Earth and the sun. Now, Halley was pretty old at this time, and he knew that he wasn't going to survive until long enough for this to happen. So he actually had to sort of have a personal mission to try to make sure that the younger astronomers would understand how important this was, would know about the event, and to be able to do the work to make this measurement. Now, why was this measurement so difficult? Well, you couldn't do this measurement in just one place. You had to travel across the globe because it wasn't one measurement of Venus motion that would illustrate this. It was multiple measurements that you needed, and they all had to be taken at the same time across the globe. So why is that? Okay. Let's take a look at what it is like to measure. Now, this is obviously not to scale. This is a very, very simplified schematic version of the solar system. We've got the blue Earth right here. We've got a green Venus, and then we've got the sun. And if you imagine drawing a line of sight from an observer on Earth past Venus and seeing it against the face of the sun, you would see it in a particular position. All right? If you then imagine an observer on a different position on the Earth, they would see that where they see Venus against the background of the sun would be in a different place. Now, since this is only happening at one moment, the only way to take a look at that is to be in those multiple places at the same time. So what would that look like? This is just a schematic of what you might see. You would see, if you could overlay it, you would see two black spots on the surface of the sun in slightly different positions. All right. So what you want to do is send observers all over the world to try to get as many measurements of this as you can. Why? Well, if you imagine that the solar system is smaller, you would see a greater difference in those positions. If the solar system is larger, you would see a smaller difference in those positions. Okay, this phenomenon is called parallax. And an object that is near you is going to seem to move more than an object that is farther away. And you can see parallax right now. I encourage everybody to do me a favor, hold out your thumb if you've got a window nearby, or even if you just do it against the wall, hold out your thumb, close one eye if you have two working eyes, and then open the other one. You can see that your thumb seems to jump back and forth if you open one eye and close the other, or if you only have one working eye, you can move your head back and forth. What you see is that because the thumb is closer to you than the background is, it seems like the background seems to move farther, or the object seems to move as you move. And by measuring out those tools, you can see that if the solar system is smaller, you will see a greater parallax of the sun and Venus. If it is further away or larger, you would see a smaller parallax. So by measuring that angle, that's what allows you to measure the size of the solar system. All right? As long as you know how far you have moved on Earth, and measuring latitude is actually a fairly accurate and simple measurement to make in this time period. All right, so why do you need to be so far away on the Earth? Well, this is a small effect that is very challenging to measure. Whenever a scientist has a small effect that is very challenging to measure, they want to do whatever they can to make sure that that effect is as large as possible. And the way to do that is to put yourselves multiple places on the globe. You can see here, if you're closer, you have a small difference. If you're further away, you have a larger difference. If you're closer, you have a small difference. If you're farther away, you have a larger difference. All right? So you want to maximize that distance, and that's why it was necessary for astronomers to travel all over the globe. Now, I want you to imagine that this is in a time where traveling across the globe doesn't mean just booking a plane ticket. It means jumping on an airplane. It means jumping on a boat, sorry, and very dangerously traveling to places where you might not have the best relations with the people that live there. So it really was an international collaboration to try to bring some of the most powerful telescopes in the world, pack them onto the dangers of traveling on a ship, take the time to build a temporary observatory, and then make this sort of measurement. All right, let me show you what this looks like in Stellarium. I showed you the view in of Mercury. Let's just see what Venus looks like. So I am going to, I think I have, this is a position in Copenhagen. So this is what it would have looked like in Copenhagen. If we back up, you can see in 1761, Stellarium reflects it pretty well. You can see there's some odd atmospheric effects here at the beginning that actually made it very, 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 very hard for them to get a good measure. And then Venus moves across the sun there and then moves out. Now, the astronomers couldn't really measure exactly where Venus was based on, because they were in different locations, they couldn't do an overlay and then measure the difference. What they did instead is they actually measured the entry and exit timing and then compared the timing to then calculate that. But this was, I mean, this was like adventure science. It was literally deadly to try to risk your life to travel across the globe. I believe 4 astronomers actually died in the 1761 to 1769 attempts to measure. 1761 didn't go very well. 1769 went quite a bit better. All right, so measuring the distance to the sun. Now, once you have that, oh wait, I think I have some images, modern day images of the 2012 transit of Venus to show you. So if we go here, this is the transit of Venus, and you can see why they chose Venus to do this measurement. It is a much larger target, much easier to measure. In fact, they did kind of try with Mercury, but Mercury was really hard to see. Let's watch that one more time. So there's Venus transiting in front of the sun on June 6th of 2012. Okay, so they did eventually get a measure. Whoops, that's supposed to say 1769, not 1768. It's issued in terms of the parallax. Their 1761 measurement was pretty rough. They had a range of 99 to 77 million miles for the distance to the sun. 1769 measurement was somewhere between 97 million and 93 million. We now measure this by bouncing radar off of the moon and Venus. The first time that was done for the moon was 1957. Second time, or for Venus, the first time it was done was 1961. There are probably other ways they measure it too, but one of the most accurate ways is to bounce radar off of Venus. And we now currently get a measure that is pretty close to what they got in 1768. And it is now, we actually now define the AU as a specific distance, but it's about 92.9 or 93 million miles to the sun. Now, as I said earlier, once you have one measurement, you now know how big the solar system is. And that allows you to use another measure. So if we see here in 1761 and 1769, we made expeditions to measure size and scale of the solar system. What that then allows you to do is measure another form of parallax, and this time we call it stellar parallax. So these are the geometric methods that we use. When you look at a system like the constellation of Cygnus, which will soon be rising high above us in the summer sky, remember that looking at these dots it's impossible to tell is this object dim because it's far away or because it's just not very bright. If you assume that all stars are the same brightness, you can estimate their distance relative to each other. But if you don't know if they're the same brightness, and trust me, stars are not all the same brightness. There's a lot of variation in stellar brightness. You have to use a combination of the two to figure out how far away they are. And that's pretty hard to do. So what you really want to do is another geometric method. Now, once you know how far the Earth is moving, you can, just like you did with Venus, cast a line of sight past one star to the very far away stars. Wait 6 months for the planet to move to the other side of the sun. So it's going to move to AU there. And then you will draw another line of sight and see that your star that is nearby seems to have moved compared to the farther away stars. So let's just illustrate what that might look like in a telescope view. You would watch, if you watch continuously, star seems to be in one position, and then the other star seems to move across the sky there. Okay, let's watch that one more time. You can see that the star seems to move, and the farther away stars don't seem to move, and you use those as your background. All right. So that gives us the definition. If you've ever heard the distance a parsec, this is very famous because they misused it in Star Wars as a unit of time because sec sounds like second. What it really means is a parsec is 1 per arc second. So 1 arc second of this angular motion is a distance that we call 3.26 light years, or 206,265 times the distance between the Earth and the sun. So if you ever heard that before, that's where that distance comes from. It's kind of a funny unit, but it just means that you know how far things are away without having to translate from your actual measurement to an actual distance. All right, this is an example. This is an animation that I made earlier today just for you guys to illustrate what it might look like if you could see parallax with your eyes. Now, this is a huge exaggeration. This is a simulation of what it would look like if we drastically exaggerated what parallax would look like. So you may not see much, but watch this star right here, this bright one that I've just circled with my pointer. Ignore this, this is just the sun. Now in a moment, we're going to start letting the stars draw lines. You can see that this is simulating the Earth moving and seeing how all the other stars seem to move as the Earth moves. And you immediately understand this star is the closest, this star is second closest, and these other stars are much farther away. And we'll fade that away, and I'm going to speed it up. And of course, it moves in a cycle. As the Earth moves around the sun, it makes it look like these stars seem to wobble back and forth. And we'll speed that up again. And now you can really get a sense that the universe really is 3D, right? This is one of the ways we measure the distance to stars that are relatively close to the Earth. Okay, I think it's worth it to watch that again. I'll try to be a little more quiet this time. Now, if you track this one, you can see it seems to be moving compared to this further away star nearby it. Remember, we're just watching the apparent motion of these stars because the Earth is moving, and that's called parallax. Speed it up again. Watch as they really wobble. Now you can really see that 3D nature of the sky. Okay. Let's move on. We do still use parallax today. Now we typically measure it with satellites because getting them above the atmosphere really helps. There was a mission called Hipparcos that ended in 1993. It measured the distance and parallax of 118,000 star systems, some of which were single stars, some of which were binaries, which is why we don't just say 118,000 stars. Gaia is a currently active mission that launched in 2013. It is primarily an ESA mission. I believe NASA has also partly funded that, but I haven't double checked that. It is measuring 1 billion star systems. So you can see the change in technology between 93 and 2013. In just 20 years now, we can effectively measure the parallax to 1 billion star systems. And that really is allowing us to map the galaxy in a way that is really accurate. But parallax doesn't get you outside of the galaxy. So then, and that's sort of the end of the geometric methods. There are other geometric methods. All of those work kind of within our galaxy and even really pretty near the sun. To try to measure the distance to something much farther away, you need a different technique. And I am running out of time, so I'm going to go quite quickly here, but that's okay. So if you have something like a candle, pretty much all candles are roughly the same brightness. If you see it further away, then it will appear much dimmer. So you can see these much further away candles are much dimmer. So what we need to find is an object in astronomy that we can measure how bright it should be. So then by looking at how bright it appears, you can determine how far away it is. If it's very bright, it must be close. If it's very dim, it must be farther away. So once you know once you have a tool or a technique or an object that you can say, oh, it should be X bright. If you see it as X divided by 1,000, then you know that that's how far away it is. So we need to find some object that matches this. So this was done, remember that the distance to the sun was measured in 1639, relatively accurately. Sorry, in 1769, I'm sorry. It wasn't until 1838 that we got a sense of how far away the stars were. And then in 1912, say 80 years or so later, Henrietta Swan Leavitt discovered the period luminosity relationship in Cepheid variable stars. That is going to be our standard, our first standard candle. So this is a plot. And on the bottom, it says phase, but you should think of that as time. And then on the right, this is the brightness of the star. So you can see, don't worry about the fact that the numbers are a little weird there. You can just see that a star dims and then brightens and dims and then brightens in a very regular way. This is just some examples of these stars. These stars, what Leavitt realized as she was studying the small Magellanic Cloud, here's a pretty picture of it there. She realized that if she plotted how long it took those stars to pulsate, she could tell you how bright they were. So this is a page from her initial paper that showed that right here we have how long it takes the star to pulsate. This is how bright the star is. And the longer it takes to pulsate, the brighter it must be. So what that does is that gives us a hook. There's a thing that we can measure because we can measure it pulsating as long as we can see it. And by figuring out how long it takes to pulsate, that tells us how bright it should be. And then by seeing how bright it appears, that tells us how far away it is. And these stars are typically quite bright, so we can see them at very large distances. And this is an image. This is the original plate whereby Edwin Hubble figured out that M31 had a variable star in it, and he could use that to estimate its distance. And he estimated that distance, or we now feel that distance, measure that distance to be around 2.6 million light years. I apologize for the airplane. It's 90 degrees, so I have the windows open, and it's I live close to the airport. All right, so 2.6 million light years away. And that settled that debate that astronomers were having. And I want you to realize how powerful this measurement was. First, we have the Earth at the center and the planets moving around it. Then we realize that the sun is really at the center, but we have no idea how big the cosmos is because we don't know how far away it is. Then we realize that the sun is about 93 million miles away, but we don't know how far away the stars are. Then we learn that the stars are light years away to tens to thousands of light years away. But we don't know if that's it, if the Milky Way is everything, and all of these little fuzzy blobs we're seeing are within that Milky Way. At this moment, we realize that the universe is very, 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 very big, far bigger than most had really believed it to be. And it was by clever techniques in measuring how bright something appears to be, and then figuring out how bright it should be, and then estimating how far it is away. Here's a modern picture of the Andromeda Galaxy. This actually is a galaxy that you can see without a telescope if you go to a very dark place. It is near the constellation of Pegasus. It will be visible in the late summer and fall. After figuring out that some of these galaxies were obviously very far away, Hubble was able to figure out that, the further away you looked, the faster galaxies seemed to be moving away. And that connected the mathematics that general relativity had predicted to what we were actually seeing in the universe in a way that hadn't been done before, and gave us another way of measuring the distances to objects. One of our latest standard candles is a thing called a supernova. It's a big, bright explosion, a type 1a supernova. It's a very standardized brightness explosion, or at least a calibratable. This is an animation of all of the supernovae from around the 1800s until, say, 2015 or so. And I know you're not seeing anything yet. You should pretty soon being able to see flickers. Over time, as we have gotten better at detecting these objects, we detect more and more of them. And so it's as though there are convenient flashbulbs going on throughout the universe. And by looking at those flashbulbs, measuring how bright they seem to be, we can measure how far away the galaxies that they are a part of are. And that allows us to calibrate Hubble's constant, allows us to measure the shape and structure of the galaxy just by watching these flashbulbs throughout the cosmos. All right, I'd like to end here with the Hubble Extreme Deep Field. On the left there, you see an outline next to the size of the moon, just to give you a sense of how big this spot on the sky is. When you look with Hubble at this image and just take data for as long as you can, you find 5,500 galaxies in that tiny little spot. We now can see that we see a small number of galaxies nearby, more and more further out, and then more further and further away. And it's by these techniques that we can measure the distance to those galaxies and really calibrate how big our universe is. So to remind you, light minutes away are the planets, the asteroids, the comets, and other things that you might think of. Further out are the stars. They are light years away. Many of the nebulae and clusters of stars that you might see fun pictures of are light years away. Galaxies are hundreds of thousands of light years across and millions of light years apart. And the edge of our observable universe, the size of it that light has had time to get to us, is about 46 billion light years across as we would currently measure it today. So I'm happy to stop the screen sharing. And Jonathan, if you would like to let me know about questions. I think I've gone a little long, but hopefully we have a little more time for questions. Okay, any questions?
We absolutely do. Thank you very much, Keith. As a reminder for questions, if you're on Zoom, you can use the Q&A or the Google form link I sent out before. And if you're on YouTube, you can either post them in the chat or use the Google form link as well. We already have a few, so I'm just going to delve right in.
Okay.
You obviously talked about Mercury and Venus transiting. Do we see any of the other planets transiting or any other objects? You know, there's been comets and things in the news recently. Do we ever see those kind of transit in front of the sun?
That's interesting. All right. Well, I'm actually going to share my screen again to illustrate this because I think it's best if I show you. So let's go back to that NASA's eyes. So if we take a look here, one of the things that you will see is in terms of the planets, Earth is the third out from the solar system. So if I move times forward, oops, not that one. If I move times forward, you can see that the only planets that ever end up being in between Earth and the sun are Venus and Mercury. The other planets, because they are outside of our orbit, they can never be in between us and the sun, so we cannot see them transit the sun. However, we could see other objects like asteroids or comets transit the sun because they could have orbits that take them in between sun and the Earth. I don't know if we've ever seen that. We probably have. I do know, let's see, I might actually have another PowerPoint slide open. No, I think I closed it to minimize resources. If you go to APOD, you can see that there are images of the space station transiting the sun that are actually really pretty. And there are images of some of our space probes transiting the sun as well. There's also a lovely image of the Parker Solar Probe passing behind the sun, which is kind of a neat little thing to see as well. So Mercury and Venus are the only planets that can pass in between Earth and the sun and therefore transit it. The others are never in between us because their orbits are larger than Earth's. Other objects theoretically could, but I don't know if we've actually measured that.
Yeah, I was going to say, so if you are interested in pretty astronomy pictures, Astronomy Picture of the Day, or APOD, I think it's apod.nasa.gov, but search engines will pick it up as a new picture every day. So if you are interested in getting pretty astronomy pictures, it's a great way to sort of be exposed to a few of those. So I do encourage, just like Keith said, go take a look at them. Coming back to parallax and the stars. So there's two kind of questions with that. Can you see parallax effects of the stars with the naked eye? You know, if you went out, the Earth goes around the sun, you know, can you see it between seasons with the naked eye? And secondly, kind of linked, you talked about Gaia. What happens if stars are moving? And that ties into Gaia as a little bit for perhaps one of the answers there.
Yeah, excellent question. So in terms of can you see it with the naked eye? Absolutely not. In fact, early on when it was proposed that the Earth could be moving, Tycho Brahe tried to measure the parallax of stars, and he was very good at measuring the motions of things in the sky, but the actual motion is so small because they're so very far away that he couldn't measure it. And so he said, well, if I can't measure the parallax, they clearly can't be that far away, so the Earth must not be moving. Tycho was a very smart astronomer, but he actually used data to reason that the Earth wasn't moving. What he didn't realize is that the stars were so far away that not only could you not see it with the naked eye, he also couldn't measure it with his tools. It wasn't until much later that their tools were accurate enough to measure that. So you cannot see it with the naked eye. However, I will point out that we talk about parallax in terms of astronomy, but it's important to remember that you see parallax when you're driving in the car, right? You see parallax when you walk around. In fact, you use parallax to keep from running into objects every day, but you learned how to do it with a toddler and nobody bothered to tell you what it was called, right? So parallax is just that geometric phenomenon, but we use it to measure things in astronomy. So about Gaia, what do you do if stars are moving? Well, what you do is you measure the position of the star very, very accurately, and then look for a cyclical measurement that is the result of the motion of the Earth around the sun, and then sort of separate that out from what's called the proper motion of a star, which is its actual 3D motion or really proper motion is actually its motion projected on what we call the sky, which is an imaginary 3D bubble around us. That's the technical term of proper motion. But if you want to think of like real motion is the actual motion of the star, because the stars are moving, they just move really slowly. A system like Gaia is designed to be able to tell the difference between a periodic motion of the Earth and the satellite's motion versus the non-periodic motion of the star actually moving in space? So yeah, that's an excellent question. You do have to separate that out.
I think just to add on that, there was a fantastic movie that came out from Gaia that, because they've measured the motions of these stars, they can predict how the constellations and things will change over time. So if you search for that, you get to see Orion being ripped apart as the stars in the constellation moves. It's quite a nice little video you could actually find online as well if you'd like to take a look at that. Another question. So slightly skeptical question here.
Mm-hmm.
How sure are astronomers that standard candles really are the same brightness?
Yeah, so how sure are astronomers that standard candles are really the same brightness? So I'll answer that in two ways. One is astronomers actually argue about that a lot. And what that means is that we do several things. One, we find places where several of these are in, say, the same galaxy. So, you know, relative to the distance from us, their variation in distance is really, really small. That was largely how Leavitt figured out that Cepheid's period was related to their brightness. So she found a bunch of stars that she didn't know how far away they were. She knew they were quite far away, and that they were all close to each other, and that their distance from us was huge compared to their variation in distance amongst each other. So you'll find examples in the same area. The other thing you do is you try to understand the object itself. And to do that, we both study it physically by looking at its data. We also, or the data we get from it, we also do computer simulations to try to figure out if we really understand what this object is and what conditions could cause it to be different, right? And then the second part is, it's important to remember that whenever an astronomer, or really any scientist, measures something, they don't just get that number and say, there, that's the number. What they do is they say, here's the number we measure. Based on our best understanding, it could be this much bigger, or it could be this much smaller. And that is called the error bar, or the, I guess error bar is really the right way, or just standard difference is sometimes used. But so when an astronomer quotes a number in a scientific paper, they don't do what we do giving public talks. They don't just tell you the number. They say it's this plus or minus this amount. So you might say it's 93 million miles plus or minus 500 meters, right? That means we feel like we've got a really good measure. Or we, as you saw, the numbers I first quoted for measuring the parallax of Venus, they said, well, based on our best analysis, it is somewhere between 77 million miles and 94 million miles, or whatever the numbers were. So it's important to remember that, and so we do our best to shrink those, but we do build our models of the universe knowing that our measurements are not exact, trying to do our best understanding of just how non-standard those standard models can be.
Excellent. Well, I think we'll leave it there because that's the questions we've had in. So the recording of tonight's talk will be available on YouTube in the next few hours once it's gone through the processing. And you can also find the recordings of our previous talks online there as well. This is actually our final talk we'll be having online at the moment. We normally take a pause at the end of the university semester, so it's our usual time for that, and it also gives us a bit of an opportunity to coordinate the program moving forward. I'd like to take this opportunity to thank all of the speakers we've had over the last few weeks. They've all done a fantastic job of adapting to the current situation, and I hope you've enjoyed the talk both tonight as well as over the previous weeks. Given the present situation and the policies, obviously it's going to keep evolving in the coming weeks, and we'll adapt to that as best we can to keep you all engaged with science. It's not clear at the moment whether we'll be able to when we'll be able to welcome you back onto campus at Notre Dame for in-person events. But we are actively working on some exciting ideas for virtual events, including possibly virtual stargazing as an option, and we're looking into that at the moment and the technology we would need to do that, as well as looking at some other options for online discussions and talks. As a reminder, you can find out all of the information about that on our series website, which is nduniverse.org, and it will all be posted there when it becomes available. And we also have our mailing list there that will be advertising those events, as well as Keith mentioned at the beginning, his mailing list about the DVT for when we're able to do events there and other events he may be doing moving forward. For those of you who are watching further afield, don't worry. We are actually looking for, when we have our events return to an in-person format, having some way to either record those or stream them live for you. So don't worry if you're watching and can't return to campus or visit campus. We will try and make sure we have an online presence as well. But in the meantime, all that's left for me to say is thanks again to Keith for his presentation this evening. Thank you all very much for joining us tonight and over the last few weeks. Stay safe out there, and we'll see you back online or in person, hopefully, later on this year. So thank you all very much for joining us, and bye-bye for now.
Thank you very much.